Can everyone see my screen? Okay.
Yeah.
Awesome.
Lily, I don't think the volume is shared from the video.
It's not? Oh, it could be because I'm on my headphones. Let me try that again.
So when you click to share your screen, there's like a thing there's a box where you have to share the audio as well.
Oh, okay.
So if you stop screen sharing and then do it again, when you do screen share in the bottom left, there's a thing you have to click to get shared audio.
Okay. Okay, so we'll try this again. Welcome to a C-CAS tutorial on how to use Python to generate a free energy reaction profile. Hi, I'm Liliana Gallegos. I'm a third-year graduate student in the paint group at Colorado State University. And today I will show you how I use GoodVibes to produce a reaction energy profile with simple and easy commands on the terminal. As a computational organic chemist, I want to spend most of my time studying and understanding the reaction activity of interest. So automation tools that can streamline my data analysis are essential for my research. In the real-world application of computational chemistry, some of the challenges associated with making a reaction profile includes the different types of software packages used to collect our chemical values. In today's study, different software programs were used for the optimized structures such as Gaussian, while using Orca for its single-point corrections. We also have to consider whether we use multiple conformers. Performing a Boltzmann average to each of these species might be an overwhelming and tedious task. Are there specific reaction conditions that we will need to consider for our analysis? Also, we might need to correct for certain vibrational frequencies and statistical thermodynamics. All of this analysis might traditionally be done with a spreadsheet, which often lead to human error. Therefore, a Python-based workflow would be advantageous in the ease of reproducibility and reliability for building a free energy profile for every research project. So look no further because GoodVibes can handle output files produced from these different calculation types. It currently supports outputs from Gaussian 09 and Gaussian 16, Orca 4 single-point energy calculation files, as well as Cosmos solvation outputs. In a quick summary, GoodVibes is a Python-based program used for obtaining thermochemical values using corrections of the quasi-harmonic approximation, as well as other corrections for the overestimation of the zero-point energy, multi-conformer ensembles, as well as standard concentrations. To read more about it, check out the article listed below. GoodVibes has been implemented in many informatics and mechanistic studies. Some of these include organic catalysis, photocatalysis, and inorganic structure characterization. Now, I'm using a Mac computer, but these same commands also run on a Windows or a Linux computer. Okay, so let's get started. To download the program, you can Google search NSF C-CAS to find our GitHub. Here you can use any of our open source programs for any of your research needs. You can easily install it with pip or conda, just as shown here. For this video, we will look closely at the heterobiaral coupling reaction using a pentacoordinate P5 system. This work was published in Science in 2018 by the McNally group at CSU, in where they found excellent yields of the biaral coupling product of the electron-deficient pyridine ring system. You can imagine the formation of these two conformers with either the protonated pyridine in the axial position or the phenyl ring. The quantum mechanical calculations revealed the transition state structure as having the pyridine system migrating and coupling with the equatorial pyridine. This forms intermediate 2, and following the release of the pyridine coupling product. Now, you can also imagine this same mechanism happening to the phenyl ring system. This mechanistic investigation included collecting optimized structures with DFT in Gaussian and the single point calculations with coupled cluster theory in Orca using a solvation model. For a complete analysis, multiple conformers were collected for each species. Now we are ready to analyze all of our data. We first need to access the folder with the optimized Gaussian and Orca files. These are my raw output files. In this folder, I have all of the intermediates and transition structures. These single point correction files can be distinguished and read by adding DLPNO to the end of the file. In order to obtain a reaction energy profile, we next need a YAML file to specify the reaction of interest. In this first section, we have the proposed mechanism going from reactants to the transition state, then to the product. These should match the species in the second section in where we list the name of the file to read. So I'll edit those now. This last section includes all of the plot formatting options to personalize your reaction profile. Since we are modeling two reaction pathways, I have selected black and a teal color. Our final step includes running good vibes through the terminal. I will move into the folder where I have all of my files. Using the Python command, I will include arguments like calling the good vibes program, grab all of my optimized Gaussian files, select the option to add single point corrections with marked DLPNO at the end of the file. I will call the YAML file to read the arguments for the potential energy surface option and for plotting. Additional options for this specific reaction include adding the reaction temperature at 80 degrees Celsius. I'll put all of the imaginary frequencies in my files, and convert any small stubborn imaginary frequencies that are less than 5. And finally, we select the media to put ethanol at a concentration corresponding to liquid ethanol based on its density and molar mass. The last option converts the concentration for all of the species to 1 molar. This is currently running in real time, and in a few moments, I will get my full requested analysis. Here we go. In a compiled table, the program outputs an uncorrected delta G column in addition to the quasi-harmonic corrected values in the last column. Here are my imaginary frequencies for my transition states and my solvent media. And down here, I have my reaction for the phenol pathway and pyridine pathway. Here, I can see the delta G values in kcal per mole for comparing each pathway. Now let's look at the graph generated. Here we have a clear comparison of the relative energy pathways. We can see the reaction energy barrier for each of them, but we can also zoom in. We get a clear view of the Boltzmann conformer distribution for each intermediate and transition state. We can select to save any of the zoom views. We also get the saved PNG file in our original folder. And now we can show it off in our next research presentation. Voila! Our mechanistic investigation concludes that the reaction barrier for the formation of the pyridine coupling product is favored by 8 kcal per mole. Thanks for watching this video. I hope you enjoyed it. Stay tuned for our next C-CAS tutorial. Bye!
How do you have so much energy?